So water is amphoteric. Remember, amphoteric means it's something that can act as either an acid or a base. Autoionization. Well, auto refers to something doing it within itself, right? Ionization, forming ions. So this is the process by which water can act as an acid and a base with itself. How's that for weird? So we looked at these reactions. Here we have ammonia with water, and here water is acting as the acid. It's going to donate a proton to the ammonia, forming ammonium ion. We looked at water acting as a base. Here we have an acid. It's going to donate that hydrogen to the water. The water accepts it like the babysitter that it is and holds on to it. Okay? Very, very weird thing. Water can do that with itself. One water says, I'm tired of holding the baby. I know you have your own baby. Would you take mine, please? Right? So the base accepts the proton from the acid, and we end up with H3O plus and OH minus. Does that seem like an unlikely thing to happen? I mean, here we've got this transfer because one of them is a base and really wants to take the hydrogen ion. But here we have two identical things, right? We don't often see two identical things becoming two different things, right? It's weird. This happens, it only happens a teeny tiny bit, okay? So if we take this equation here and we use H plus instead of H3O plus, then we can make it look simpler and say that H2O liquid is H plus OH minus. We are more familiar with looking at this in the opposite direction. We've got an H plus and an OH minus. They're going to stick together and form water. Well, that's true. But this is in an equilibrium. So it's an equilibrium, so there has to be an equilibrium constant. Right? So here's that simplified one. And so we've got H plus times OH minus divided by the reactant's a liquid. So the the equilibrium constant here, H plus times OH minus. Or exactly the same, just looks different, H3O plus times OH minus. And this is given a subscript W, and it is essentially the ionization constant for water. We call it the ion product constant for water, Kw. You don't really need to know the name. It gets called different things sometimes. You need to understand that Kw refers to water, and K is an equilibrium constant. So this is an equilibrium constant for water. At 25 degrees Celsius, which is kind of like a standard room temperature, which I think is a little bit warm, but whatever, that equilibrium constant is 1.0 times 10 to the minus 14. It's pretty small. There are smaller equilibrium constants, but this is pretty small. So what this means is, in pure water, we're going to have the H3O plus concentration be equal to the OH minus concentration. Because when one water molecule ionizes, it forms one of each of these. So these have to be equal in concentration. Does that make sense? It's like a pair of shoes and you split them up. You've got one left shoe and one right shoe. Doesn't matter how many pairs, if they're actually pairs, you're going to have equal numbers of right and left shoes. So those concentrations are equal. And so if we call this x and call that x, we can solve and find out that those are equal to the square root of kW, which is 1 times 10 to the minus 7. So that's moles per liter. That's a very, very small concentration. So the concentration of ions in pure water is very small, but it is not zero. Pure water is said to be neutral. It's not acidic or basic because the concentrations of these are equal. So it's not acidic or basic. Any questions? So an acidic solution, we've put an acid into it, and the acid creates additional hydronium ions. Well, that ion product constant for water is still going to apply. So the concentration of hydroxide decreases. The equilibrium is going to shift towards the reactant, and we end up with the hydronium ion concentration being greater than the hydroxide ion concentration. Carried away with the parentheses there. So there's the ionization for water. If we put more H plus in, what does that do to the equilibrium? Equilibrium is like, hey, you gave me more acid, I don't like this. I'm going to shift in a way to reduce that. So if we add product, it's going to shift towards the reactant. When that happens, the hydroxide ion concentration is going to go down a little bit. We've added H+, the hydronium ion concentration is greater than the hydroxide ion concentration. The equilibrium is going to shift, but it cannot completely take care of it. Basic solution is kind of the opposite. You put a base in it, you add a bunch of hydroxide ions, the equilibrium is going to shift again. It's going to shift to the left. But the hydroxide ion concentration is still greater than the hydronium ion concentration. So acidic solution, hydronium concentration is greater than hydroxide. Basic solution, the opposite. The hydronium ion concentrations of 3 solutions at room temperature are as follows. Which solution is acidic? Well, we just learned that an acidic solution, which one is larger, the hydronium ion or the hydroxide ion? The hydronium ion, the acid one. So that is bigger than the hydroxide. It's like, well, that's great, but this is just telling us the one thing. Well, what's true for pure water? These are equal to each other. And they equal 1 times 10 to the minus 7. That's the square root of 1 times 10 to the minus 14. This is a good number to remember. Okay, so which one of these is acidic? A. Yep, A is correct. Here, the concentration of hydronium ion is larger than in pure water. We could figure out what the hydroxide ion concentration is, but we don't need to identify whether this is acidic or basic. This has extra hydronium ions. Letter C, now we have fewer hydronium ions, so what kind of a solution is that? It's basic. So this one's basic, and this one was acidic. What's the one in the middle? It's neutral. Any questions? Calculate the hydronium ion concentration at 25 degrees Celsius for each solution and determine if the solution is acidic, basic, or neutral. We could determine whether it's acidic, basic, or neutral just by looking at the hydroxide ion concentrations, but that's not what it asks us to do. So we know that Kw is equal to the hydronium ion concentration times the hydroxide ion concentration, and that is equal to 1.0 times 10 to the minus 14. So if we are looking for the hydronium ion concentration, we could rearrange this equation. The hydronium ion concentration will equal Kw, 1 times 10 to the minus 14, divided by the hydroxide ion concentration. So let's do that for A. I'm going to divide by the hydroxide ion concentration. And this is where you can get into trouble if you're not using scientific notation correctly on your calculator. So I would call that 6.7. Actually, H3O plus equals 6.7 times 10 to the minus 13 molar. Any questions about this over here? That should seem delightfully simple compared to what we were doing with quadratic equations and solving for x. Is this solution acidic or basic? It's basic. Hydroxide ion concentration is bigger than the hydronium. What's the hydronium ion concentration for this one? Well, it's going to be 1.0 times 10 to the minus 7. You could do the calculation, but this is pure water, and so they're equal. So is this acidic, basic, or neutral? Neutral. Let's do this one. So I'm getting 1.2195 times 10 to the minus 5. 1.2 times 10 to the minus 5 molar. Acidic, basic, or neutral? Acidic. Because the hydronium ion concentration is greater than the hydroxide ion concentration. So this is kind of an example of what I asked you to do in lab, showing your work. Here, we did 3 calculations that were the same, right? So the first one, I wrote everything out. The second one, we can just assume that I plugged these numbers in the same way, did the math, and got the answer. If you want to write all of them out, that's fine. The minimum is show one example of each kind of calculation. So I'm sure you've all heard of pH, right? And they taught you about this in Chem 3A, but it may be a fuzzy memory. So we're going to learn a little more about it. So the pH scale is just a compact way to specify the acidity of a solution. So the definition is pH is equal to negative log of the hydronium ion concentration. So that P stands for negative log of. So if we have a solution with hydronium ion concentration equal to 5.3 times 10 to the minus 8, then the pH is going to equal the negative log of 5.3 times 10 to the minus 8. It's got to be base 10 log. You get the calculator to show you that number? So, sig figs. I'm not going to hammer you on this, but I would like you to ponder it and try to remember it. When we have a logarithm like this, only the numbers to the right of the decimal point are considered significant figures. The numbers to the left are essentially placeholders for the decimal point. So the pH here with 5.3 times 10 to the minus 8 is this. I can tell you what the pH for, let's say, 5.3 times 10 to the minus 6. That's going to be 5.275724, blah, blah, blah. Can I do logarithms in my head? Absolutely not. This number is related to that number. This is one less than that. This is one less than that. The 5.3 part is all after the decimal point. Okay? So this number has 2 significant figures. That means we keep 2 decimal places over here. So we would call this 7.28 for the pH. And I really want to point that out because a lot of times, it's like, oh, we'll just round it to 2 significant figures, right? This has 2 sig figs, and so we're going to call this 7.3. Well, no, now you've rounded it to 1 significant figure. So if you're going to make a mistake with sig figs, make the mistake of writing too many, right? So when you do a calculation, always write down more than you need. The minimum is 2. Just write down 2 extras, and then round it the way you think it should be rounded. Then if that wasn't right and you need to include more or less, you can go back here and do it very easily. Any questions? So here's a pH. A pH of 7. Oops. When the pH is 7.0, that means the hydrogen ion or hydronium ion concentration is 1.0 times 10 to the minus 7. When this part of the scientific notation, the coefficient, I think, is a 1, then the pH is the exponent made positive. So over here, that's going to be 10 to the minus 14. And down. So we can identify whether this is acidic or basic by looking at the hydronium ion concentration or by looking at the pH. So just going back here for a minute. If the pH is less than 7, the solution is acidic. If the pH is more than 7, it's basic. So here the pH is 8.02, acidic or basic? It's basic. Well, here we're given the hydroxide ion concentration and asked for the pH. But the pH uses the hydronium ion concentration. So we have to do a calculation similar to one we did earlier. So KW is 1.0 times 10 to the minus 14. We're dividing by 7.1. 1 times 10 to the minus 3. So that gives us 1.4085 times 10 to the minus 12. And so that's what I can use in my pH calculation. I'm going to carry those extra digits. In fact, I'm going to grab the whole thing in my calculator. And I'm going to get 11.8513 or 11.85. Acidic or basic? Also basic. Any questions? We need to be able to do all the various permutations of calculating hydronium, hydroxide ion, pH, POH. Okay, here's the one I was getting ahead of myself with. Calculate the hydronium ion concentration for a solution with a pH of 8.37. Well, pH equals negative log of the hydronium ion concentration. We've got the pH, but we want this. We need to rearrange this equation. You could use a solver as well. So to rearrange this equation, what I'm going to do is I'm going to multiply both sides by -1. And then I'm going to take the antilog. So 10 to the minus pH is going to equal the hydronium ion concentration. So hydronium ion concentration equals 10 to the negative 8.37. Your calculator doesn't care that you're raising something to a non-integer value. So I like to use the 10 to the x button for this, because that's what it was made for. But you can also use 10 and caret negative 8.37. How many significant figures should this have? How many does this pH have? It's got 2 decimal places, yeah. So 4.3 times 10 to the minus 9 molar. Oh, good question. Shouldn't it be at the 6 instead of at the 2? This is the log, so only after the decimal point do they count. This is not the log of a number, and so regular sig figs apply. So pHs, you don't count the numbers before the decimal point. Everything else, regular. Good question. Any other questions? So the pOH scale is defined with respect to hydroxide ion. pOH is just the negative log of the hydroxide ion concentration. So P is a mathematical operator that means negative log of. You can also have P calcium, which is the negative log of the calcium ion concentration. We're just going to see pH and pOH. We can also take an equilibrium constant and take the negative log of that and get pKa. In that table of acid, it gave us Ka values and it gave us pKa. pKa is just the negative log of the equilibrium constant. It's convenient because it takes the concentration or the equilibrium constant range down from like 1 to 10 to the minus 14. It's a huge range. And now we're looking at 0 to 14. Oops. Bless you. So derive the relationship between pH and pOH. I'm not going to ask you to do this, but I just want to show it to you. So, bless you. So pH is the negative log of the hydronium ion concentration. What does the hydronium ion concentration equal in terms of hydroxide? Well, let's do it this way. We know this. So we could take this equation and solve it for H3O+. So I'm going to take this and put it in there. The negative log of Kw over the hydroxide ion concentration. When you take the log of two numbers that are divided, it's the log of the numerator minus the log of the denominator. So this would be equal to negative log Kw plus the log of hydroxide. Should have done that on another line. So pH minus the log of the hydronium ion concentration is equal to the negative log of Kw. Kw is 1.0 times 10 to the minus 14. What's the negative log of that? 14. 1 times 10 to the minus 14. The log of this is negative 14. Negative 1 in front gives us a 14. What's another right way of writing negative log of hydroxide ion concentration? POH. pH plus POH equals 14. All this mess, and it comes down to that. That's not something, like I said, that you need to be able to do. Okay, so this brings us to the circle of life, the circle of pH. Is the Lion King theme song running in your mind? Yeah, I should have it playing in the background or something. So we've talked about pH, we've talked about hydronium ion concentration, hydroxide ion concentration, and POH. These are all related to each other by the circle of pH. So if I have pH at the top, from the pH, I can calculate the hydronium ion concentration. If I have the hydronium ion concentration, I can calculate the pH. So, hydronium ion concentration is equal to 10 to the negative pH. pH equals negative log of hydronium ion concentration. Okay? If I have the hydronium ion concentration, I can calculate the hydroxide ion concentration. Because I know that the hydronium ion concentration times the hydroxide ion concentration is equal to Kw, which is 1 times 10 to the minus 14. So we can go either direction here. And then the other one is POH. And the relationships between POH and OH are very similar to pH and H3O+. So the hydroxide ion concentration is equal to 10 to the negative POH. The POH is equal to the negative log of the hydroxide ion concentration. And we just looked at the relationship between pH and POH. pH plus POH is equal to 14. I present to you the circle of pH. So, why talk about this? There's going to be a lot of times when you need to convert, right? You're given pH and you need this. Okay, no big deal. But what if I have this and I'm trying to find the hydroxide ion concentration? There's not one equation to do that. Could you write an equation? Yes, I'm sure you could. But it's just not worth doing. So, to get from pH to hydroxide ion concentration, you have to go one way around the circle or the other. So you can go around this way, You can find the hydronium ion concentration, and then you can use this guy to find the hydroxide ion concentration. Or you can go the other way. POH is just 14 minus the pH, and then you can use this guy. You can do either. The one you do is up to you. I prefer going to the left here because I like this better than that guy down there. But it's a matter of preference. Okay? So if you have two things next to each other, you can convert directly between them. If they're across from each other, there's going to be a step in the middle. How close are we to the end here? Oh, good. Very, very close. So as the pH of a solution increases, meaning it gets larger, what happens to the acidity of the solution? It decreases. Acidity and basicity are inversely related. When one goes up, the other goes down.